Hi guys, up to now we have seen the 180 degree conduction mode of the 3-phase inverter. In this we have seen various quantities related to phase and the line values. So we have seen most importantly two quantities, that is total RMS and the fundamental RMS voltages. In phase the total RMS is root 2 by 3 VDC and line is under root 2 by 3 VDC. And fundamental is root 2 by pi VDC. Here it is root 6 by pi VDC. Okay. And then we derived the current. I phase was VDC root 2 by 3R. Thyristor current was VDC upon 3R. Then we also saw RLC load, in which we derived that the diodes conduct for an angle of phi and thyristor will conduct for an angle of pi minus phi, where phi is the angle by which current lags the voltage. Phi was actually tan inverse XL minus XC upon R. Is it fine? So that is what we covered in last lecture. In this lecture we will be focusing on 120 degree conduction mode, but before starting that we must understand why we go from 180 degree conduction mode to 120 degree conduction mode. Actually, if you remember 180 degree conduction mode, I said each thyristor conducts for a duration of 180 degree, due to which as soon as T1 stops conduction, T4 will come into conduction, because overall both have to conduct for a duration of 360 degree. Now what happens is, somehow if there is overlap between the conduction of the two SCRs, that is, when T1 hasn't gone out of conduction, the thyristor T4 starts conduction. It will lead to short circuiting of the supply, due to which very heavy current can flow in the devices. Okay, that is why we need to provide some gap between the two conductions. We need to provide an interval in which one device can be turned off and other can be turned on, so that both are not conducting simultaneously. So what we do is we provide a 60 degree gap between the conduction of two SCRs, due to which now one SCR only conducts for 120 degree duration and rest is given as the gap between the two conduction, which leads to 120 degree conduction mode. So basically what is 120 degree conduction mode? Here each thyristor will conduct for a duration of 120 degree and rest of the 60 degree is left for the commutation. So if we see the inverter construction is same, the load will be identical, just the conduction sequence will change. So from 0 to 120, T1 will conduct, then this shaded portion indicates the area left for commutation. Then at 180 degree, T4 will start, but it will now only conduct up to 300, not 360. This 60 degree is left for commutation. Similarly, T3 will start from 120, will continue up to 240, then 60 degree for commutation, then T6, and here also T6. And T5 will start from 240, will continue up to 360, then 60 degree for commutation, again 120 is T2. So now if you see here, at any time only two SCRs are conducting. Earlier in 180 degree conduction mode, 3 thyristors conduct at any point of time, but here only 2 thyristors will conduct. So if you see, I have marked the thyristor which are conducting T6 and T1 from 0 to 60, T1, T2 60 to 120, T2, T3 from 120 to 180, then T3, T4 from 180 to 240, T4, T5 240 to 300, T5, T6 300 to 360. So let us see from 0 to 60. Now as I told you earlier also, the thyristor from the upper group, that is T1, T3 or T5, will supply current to the load. The thyristor from lower group will take the current away from the load. Now T6 and T1 are conducting. T6 is related to B phase lower group, that is it will bring the current back from the load in B phase. T1 is connected to A phase, so it will take the current in. Now we know VAB was actually equal to VDC, and here VAN is actually IZ, VBN is actually minus IZ since current is going out, due to which VAB is equal to 2IZ, which is VDC. So in this case, IZ comes out to be VDC by 2. So VAN is equal to VDC by 2. VBN is equal to VDC by minus VDC by 2. Next, let us check out the case from 60 to 120. From 60 up to 120, which devices are conducting? T1 and T2. Since T1 and T2 are conducting, T1 is from upper phase or upper group, T2 is from lower group. T1 will take the current to the load, while T2 will bring the current back from the load. Current will go in here and T2 will bring the current back. T2 is connected to C phase, it will bring the current back, that is I. Now, VAC will be equal to VDC. VAN is equal to IZ. VBN is equal to, VCN is equal to minus IZ because current is going out of C phase, due to which VAN is VDC by 2, VCN is minus VDC by 2. What happens in 120 to 180 degree? From 120 to 180, actually T2 and T3 are conducting. So T3 will take the current in, T3 is connected to B phase, T2 will take the current out. So that is VBN is equal to IZ is equal to VDC by 3, VDC by 2. VCN is equal to minus IZ, that is minus VDC by 2. And VAN, since no current is flowing in A phase, it is 0. Next, if we see 180 to 240, which devices are conducting? T3 and T4. T3 is from the upper group, it will take the current to the load. T4 is from the lower group, it will take the current out of the load. I and I. So VBN is equal to IZ, that is equal to VDC by 2. VAN is equal to minus IZ, that is minus VDC by 2. Similarly, if we find out for 240 to 300 and then 300 to 360, we can plot VAN. It actually comes out something like this. Initially it is VDC by 2, then it is 0 from 120 to 180, then it will be minus VDC by 2, then 0 from 300 to 360. This will be the A phase supply voltage, A phase output voltage of the inverter. If you want to draw B and C phase, you have to just shift this waveform by a 120 degree phase shift towards the right. So let us look at all the phase and the line voltages. So this is, we have marked the conduction sequence that I just explained to you. Now VAN was VDC by 2 and minus VDC by 2. Up to 120 it is VDC by 2. Then 180 to 300 it is minus VDC by 2. Now shift this waveform right by an amount 120 degree. So start it from 120. This is 120. So it is started here. Then it will go to 0. Then negative. This negative will be reflected here also. To draw VCN, start this waveform from 240 or shift this VBN waveform by 120. This will be lying here. Then 0, minus. Remember, between the plus and the minus VDC by 2, there will be a gap of just 60 degree. So if you are drawn plus, then just draw the negative one. Give a phase shift of 60 degree or a gap of 60 degree and draw it for a duration of 120 degree. Every phase voltage, positive or negative, will exist only for 120 degree. So each phase voltage is positive for 120 degree, negative for another 120 degrees. Now if we want to draw the line voltage, suppose I want to draw VAB. From 0 to 60, VA is VDC by 2, VB is minus VDC by 2. Difference will be VDC. 60 to 120, VDC by 2, 0. Difference is VDC by 2. 120 to 180, 0. VDC by 2. Difference is minus VDC by 2. 120 to 180 to 240, minus VDC by 2 plus VDC by 2. Difference is minus VDC. Okay. Then 240 to 300, minus VDC by 2, 0. So it is minus VDC by 2. Then 300 to 360, it is 0. Minus VDC by 2, it will be plus VDC by 2. Now once we have VAB, we can draw this for VBC by shifting by 120 degree. So if you shift by 120, you will start from here like this. Okay. And the rest of the waveform that will be like this will be shown here. To draw VCA, shift this VBC by 120 degree. So if VBC shifts by 120 degree, this point will come to this point. So it is like this only. Okay. So these will be the phase and the line voltage waveforms for the 120 degree conduction mode. Okay. So you have to remember the waveforms for both 180 degree conduction mode as well as 120 degree conduction mode. Now let us find out the parameters of the phase voltage in the 120 degree conduction mode. Now if you see, this is the phase voltage for 120 degree conduction mode, and this is line voltage for 180 degree. Can you see the similarity in the waveform between this and this? Just the amplitude of the line voltage is doubled, but they are exactly the same waveform. What was the Fourier series for line voltage of 180 degree? It was summation n is equal to 6k plus minus 1, then 4 VDC by n pi cos n pi by 6 sin n omega naught t plus n pi by 6. Now what will be the phase voltage for 120 degree? From this only, we have to reduce the amplitude to half. Rest will remain same. It will be 2 VDC by n pi cos n pi by 6 sin n omega naught t plus n pi by 6. This will be the Fourier series for the VAN. If you want to write for VBN, just shift it by an amount 120 degree. That is 2 VDC by n pi cos n pi by 6 sin n omega naught t plus, then 120, we have to subtract 120, it will become minus 90. That is minus n pi by 2. What about VCN? VCN can be obtained by adding 120 degrees. N is equal to 6k plus minus 1 to VDC by n pi cos n pi by 6 sin n omega naught t, then 30 plus 120 is 150, 5 n pi by 6. Okay, these are the three phase voltages for the case of three phase inverter in 120 degree conduction mode. But if I want to find the RMS value of this phase voltage, or RMS value or total RMS of the phase voltage, if you wish to find out total RMS, you will square this waveform. It will become something like this. This will be VDC square by 4. So its period becomes pi. So V0 RMS is 1 by pi VDC square by 4 into duration is 2 pi by 3 actually. So it comes out to be VDC by root 6. What is fundamental RMS? Fundamental RMS is 2 VDC by pi root 2 to make it RMS. cos pi by 6. That is VDC by pi root 3 by 2. That is our fundamental RMS. Now to calculate distortion factor, we will use fundamental RMS by total RMS. So it will be VDC root 3 by 2 1 by pi divided by VDC upon root 6. So it will come out to be 3 upon pi, which is 0.95. That means total harmonic distortion will be 31%. Okay, same as that of 180 degree conduction mode. That means even if you use 120 degree conduction mode, you do not get any benefit in terms of harmonics. Okay. Next, let us move on to line voltage. So this is our line voltage of 120 degree conduction mode. This is phase voltage of 180 degree conduction mode. If you see, the waveforms are similar, but here the amplitude is 2 VDC by 3, here it is VDC. So we can say VL 120 mod is equal to 3 by 2 V phase 180. Okay, because V phase 180 is 2 VDC by 3. If you multiply it by 3 by 2, it will become V. What about phase? If you see, this waveform leads the phase voltage of 180 degree by 60 degree because it is shifted towards the left by an amount 60. So what I can say, VL 120 is equal to 3 by 2 V phase 180 angle 60 degree. Okay, that is, it leads it by 60 degree. So now what was the phase voltage Fourier series? It was summation n is equal to 6k plus minus 1. I'm asking about 180. 2 VDC by n pi sine n omega naught t. Now you just have to multiply it by 3 by 2 and phase shift by 30 degree. So VAB in 120 degree conduction mode will become, if we multiply it by 3 by 2, it will become 3 VDC by n pi summation n is equal to 6k plus minus 1 sine n omega naught t then plus n pi by 3. That is, we have shifted this waveform towards the left by an angle 60 degree. Same way we can write VBC and VCA by shifting this waveform 120 degrees. Three VDC by n pi sine n omega naught t. 60 minus 120 is minus 60 and VCA is 3 VDC by n pi sine n omega naught t. 60 plus 120 will be 180. Okay, so this will be the 3 line voltages of the 120 degree conduction mode. Is it fine? Now if you see here, VAB is coming at an angle of 60 degree, whereas VAN that we derived has an angle pi by 6. That means the line voltage is leading the phase voltage by 30 degree. That should be the case for the star connected load. Now let us determine the overall RMS. Now what was the overall RMS here? It was actually root 2 by 3 VDC. So what will be here? We have to multiply it by 3 by 2 because all values have been scaled by a factor of 3 by 2. So it becomes VDC by root 2. So what is fundamental RMS? It is 3 VDC by pi under root 2. So if we calculate distortion factor, it is fundamental RMS by total RMS. That is 3 VDC by root 2 pi divided by VDC upon root 2. It will come out to be 3 by pi. Then what is THD? It will be 31%. Same as that in 180 degree as well as for the phase voltage. Okay. So let us summarize the relation between the phase and the line voltage similar to what we did for the case of 180 degree conduction mode. So we have two set of quantities, phase and line, total and fundamental. Okay. We just now saw the phase voltage RMS was VDC by root 6. Now if we multiply it by root 3, we will get the line voltage, that is VDC by root 2. Now if we multiply it by 3 by pi, we will get the value for the fundamental, that is VDC by pi root 3 by 2. If we want for the line, it will be 3 VDC by pi root 2. Okay. So that way you can memorize the results for the phase and the line voltage, fundamental and the total RMS. Now let us talk about the currents in case of a resistive load. In case of resistive load, I0 RMS will be V phase RMS by R. Because resistive load is a voltage step type of the load, so current and the voltage waveform will be same. So it will come out to be VDC by root 6 R. Okay. Now if we wish to calculate the thyristor RMS current, so let us look at the thyristor current waveform. This is IT. So thyristor 1 will be conducting from 0 to 120 degree. Then 120 to 180 will be for commutation. Then T4, then again commutation. So this is VDC by 2R based on the phase voltage. Now if we want to calculate the thyristor RMS, the period is 2 pi. We will take VDC square by 4R square into 2 pi by 3. Okay. So it will come out to be VDC by 2R into 1 by root 3. That is VDC by 2 root 3R. Now do not directly apply something like this, that IT RMS is equal to I phase RMS into 120 by 360. Why? Then you will end up at a wrong result. Actually, this 180 degree is reserved for T1. Though it is conducting only for 120 degree, 160 degrees kept for commutation. But actually, for phase current, half the duration is reserved for T1 and half for T4. That is why here it must be 180 degree. Then you will get the same result. Okay. So it is better if you directly derive this, not from the output RMS value. Again, power in a resistive load will be 3 I0 RMS square into R. Is it fine? So this gives the RMS value of the phase current as well as for the thyristor current. So let us summarize what we covered in this lecture. We first saw 120 degree conduction mode. We saw the waveforms for the phase voltage. For the phase voltage, the waveform was something like this. We derived the Fourier series. It was n is equal to 6k plus minus 1 2 VDC by n pi cos n pi by 6 sine n omega naught t plus n pi by 6. Then we saw the line voltage. It was actually, then we saw the Fourier series. It was 3 VDC by n pi cos, 3 VDC by n pi, then sine n omega naught t plus n pi by 3. Okay. Then we saw the relation between the fundamental and the total RMS values for phase and the line voltages. Phase, line, fundamental or first total, then fundamental. What was the total phase voltage? Total phase voltage was actually VDC by root 6. Then we multiplied by root 3 to obtain the total line voltage VDC by root 3. Well, we multiplied by a factor of 3 by pi to obtain the fundamental value. So it is root 3 by 2 VDC by pi. We multiplied by root 3 to obtain the fundamental line voltage, that is 3 VDC by root 2 pi. Then we saw the output RMS current was VDC by root 6R and thyristor RMS current was VDC by 2 root 3R. Okay, so this is what we have covered in this lecture. In the next lecture, we will see about the current source inverter. How does a current source inverter operates? This is all about your voltage source inverters, whether single phase or three phase.